Thank you.
Let's
Thank you for the
let's
introduction.
welcome.
And thank you for the introduction, and thank you to the organizers. So maybe let me first mention that there's a change of schedule, and Gabai's talk will be in the afternoon in the same room. Okay, so we define a family of Turaev-Viro type invariants for hyperbolic three manifolds with totally geodesic boundary using the representation theory of the quantum group, the so-called the modular double of UQSL2R. And we studied, we can prove that those family of quantum invariants decay exponentially with the rate, the hyperbolic volume of the manifold. That means if you want to make a volume conjecture for those invariants, that's too late. So we already proved it. But before that, let me give a quick review of the volume conjecture, and then I'll recall the definition of the Turaev-Viro invariants, the original one, and then I'll talk about our new invariants. Okay, so there are two very different approaches to studying three manifold. I mean, among many others, like symplectic topology. And one is hyperbolic geometry, following the work of Thurston and Gabai, Ego, Herman, and many others, which is very geometric. And the other one is the so-called quantum topology. So we have quantum invariants following Jones, Wheaton, Rashtikin, Turaev, Kashaev, many others. Okay. So let me use a knot complement. Let me start with the knot complement. On the geometric side, so on the complement of a knot, we can put a hyperbolic metric, which is a Riemannian metric with constant sectional curvature -1. Okay, and when the metric is complete, we call it a hyperbolic structure. And Thurston proved that most knots are hyperbolic, meaning you can put a complete hyperbolic metric on the complement. And there's a most of rigidity thing that when such a metric exists, that's unique. That means all the geometric invariants, such as the hyperbolic volume, the Chern-Simons invariant, and all different like twisted red master torsions coming from the holonomy of the hyperbolic structure, are topological invariants. So all the geometric invariants are actually topological invariants. Now, on the quantum side, we have invariants of the knot constructed from the representation theory of quantum groups. And when the quantum group is UQSL2C, we have the famous Color-Jones polynomials, okay, which is a family of z-coefficient Laurent polynomials in variable t. So they're indexed by integers. For example, for the simplest hyperbolic knot, the figure 8 knot, the nth Color-Jones polynomial of the figure 8 knot looks like this. Okay? So you see, they are very different. They look very different. One is purely geometric, and the other is purely algebraic or combinatorial. But they're deeply related, thanks to Kashaev's volume conjecture. So of course made by Kashaev, and later formulated in the following form by Jun Murakami and Hitoshi Murakami, that we have a hyperbolic knot. Again, the complement has a complete hyperbolic metric. Then we consider the exponential growth rate of the value of the Color-Jones polynomials. So let me explain. Here, you consider the nth Color-Jones polynomial of this knot K, and you evaluate at this specific root of unity e to the 2 pi I over n. In this way, you have a sequence of complex numbers, and you consider their norm. And to compute the exponential growth rate, you take the log and you divide it by n, and you let n go to infinity. And surprisingly, you see the hyperbolic volume of the complement of this knot. Okay, that's the volume conjecture. And in other words, it grows exponentially, and the volume is the exponential growth rate. Okay? So this shows that the colored Jones polynomials contain geometric information of the knot complement, at least the hyperbolic volume. And um, and the colored Jones polynomials are supposed to contain more information than just the hyperbolic volume. Why is that? Because they are they're not having the same hyperbolic volume but different colored polynomials. For example, the 5-2 knot and the -237 Pareto knot, they have exactly the same hyperbolic volume, but they have different color Jones polynomials. Okay, that means color Jones polynomials may contain more information than the volume, and we have the final expansion conjecture. I'm not sure my citation is absolute. I mean, I'm sure my citation is absolutely not correct, but I first see the term the torsion from one of Bukov's paper, and people say that everything comes from Witten. So I also put Witten here. That from the full asymptotic expansion of the values of the color Jones polynomials, you not only see the hyperbolic volume, you also see the this so-called joint twisted Rademacher torsion of the knot complement. And here, for simplicity, I put absolute value. But if you remove it, you're supposed to see the imaginary part, the Chern-Simons invariant. So that's the asymptotic expansion conjecture. And their progress. So at the very beginning, I can prove the volume conjecture for the figure A knot. And nothing was done in the next like 20 years until Ozuki proved it for the 5-2 knot, the next one. And using his method, he can prove it for all the knots with crossing number less than or equal to 7. Okay, and using the same method, Ozuki's method, Chen and Zhu can prove an infinite family of examples, the family of the so-called twist knots. And very recently, this is Dream Murakami can prove it for the family of the so-called double twist knots. So those are the recent progress for the origin for Kashayev's volume conjecture and the asymptotic expansion conjecture. So all of them actually prove the asymptotic expansion conjecture. They, I think they all see the torsion term. Okay, so that's the story for the knot complement. Now, what about general three manifold? On the geometry side, the story is almost the same. So because a hyperbolic knot complement is nothing but a hyperbolic three manifold with cusp boundary. And you consider the hyperbolic metric on the manifold, and Thurston's geometrization conjecture, later proved by Perlman, said that I mean, roughly speaking, most three manifolds are hyperbolic. And to be most precise, for every three manifold, you can canonically decompose it into pieces, and most of the pieces are hyperbolic. Okay, so you have the hyperbolic metric, and the most of rigidity still holds that once you have such a metric, it's unique, and as a consequence, all the geometric invariants are topological, such as the volume, the Chern-Simons, and the twisted Rademacher torsions. So that's the geometric side. And on the quantum side, we still have invariants constructed from the representation theory of quantum groups. Of course, the Rashtikin Turaev invariants. So for Rashtikin Turaev invariants, we need our ante closed three manifold, and we have a sequence of complex valued invariants indexed by integers, and they're supposed to mathematically realize Witten's invariance, and it is at a specific choice of the root of unity, e to the pi I over r. But at a different, so here I put a q here, it's a choice of the root of unity, and at a different root of unity, we're supposed to see other information. And we also have the Turaev-Viro invariance, which can be defined for any compact free manifold with or without boundary, um, oriented or not, orientable or not. But the price to pay is that here we don't have a complex value, we only have a real value. It's actually when the manifold is closed oriented, so that both are defined, the Turaev-Viro invariant is actually the square of the norm of the Rasch-Tigan Turaev. So they are very closely related. And for the relationship between the two approaches, the hyperbolic geometry and the quantum invariance, we have the following volume conjecture. So this is made by Qingtao Chen and myself in like 10 years ago. So I know there are thousand reasons to talk about Rasch-Tigan Turaev invariant in the Turaev-Viro, especially when Rasch-Tigan is in the room. But since later I'll talk about a new construction of the Turaev-Viro invariance. So let me use here the Turaev-Viro invariance as the example. But we have similar conjectures for the Rasch-Tigan Turaev invariant. So here, suppose M is a hyperbolic free manifold. By this, I mean it can be either closed or with cusps or with totally geodesic boundary. So there are the three, like roughly speaking, three basic types of hyperbolic free manifolds. And the conjecture is for all of them. You compute the exponential growth rates of the Turaev-Viro invariant, but you have to choose the root of unity carefully. So this is exactly not the one for the latency invariant. This is a different one. And for the invariant to be defined at this root, R has to be odd. This is a little detail. And you do the same thing. You compute the exponential growth rate, and you see the hyperbolic. In other words, the exponential growth rate is the hyperbolic form. M pi I, then you have to, here you have to put M. Conjecturally, yes. But in that case, you may see just zeros. Maybe an infinite sequence of zeros and other values. So to be very precise, you may need to take the lim suit. But for the non-zero values, you see the exponential growth. And there's the corresponding asymptotic expansion conjecture independently due to Ozuki and Gang, Ramo, and Yamazaki. So similarly, you see the adjoint twisted red master torsion. Right. For this big O of 1 over R, you can expand it as a power series of 1 over R, and all the coefficients are supposed to be topological invariants. But no one knows what those things are. Okay, and progress. For the figure 8 complement and the Vahalink complements, due to Renaud Datchery, Ivy Kafiani, and myself. So for the figure 8, and Kaho Wong, my former student, proved it for the Vahalink complement. And with Giulio Belletti and the Datchery Kafiani, we can prove it for a family of, we call it a universal family of free manifold with cusps. So the point is that for this family of free manifolds, if you do dense surgery along them, if you do dense filling along them, you can get all the three manifolds either closed or with toroidal boundary. So if you understand how the invariants behave under surgeries and together with this, you might be able to prove it for all. That's a possibility. But those are three manifold with cusps. Now for closed manifold, Ozuki proved it for manifolds obtained by doing integral surgeries along the figuring out. And to learn Ozuki's method with Kahou, we prove it for manifolds obtained from figuring out by doing all the rational surgeries. Okay? And also, um, in the last part, um, to identify certain critical value with the hyperbolic volume, Ozuki used some numerical computations, but we clarify that part. We have a conceptual proof why the critical values coincide with the hyperbolic volume. Too much details. And using the same method, Chenju, Ge, Meng, Wang, and Yang, this is not me, this is another, they can prove it for manifold obtained by doing surgery along the twist knots. Okay, so that's the progress for the volume conjecture for the Rashtikin-Turaev and the Turaev-Viro invariants. Okay, let me recall the definition of the original Turaev-Viro invariants. This is as a warm-up or preparation of our new invariant. So for simplicity, let's take a three-manifold with boundary, with non-empty boundary, so that we can take the so-called ideal triangulations. And the ideal triangulation is a triangulation, roughly speaking, of the manifold without vertices. So you take a triangulation, you remove all the vertices, and then you get the manifold. And for an ideal triangulation, we have edges and the tetrahedra. So let E be the set of edges and T be the set of tetrahedra. And for any integer bigger than or equal to 3, we define a so-called R coloring. So we assign each edge a integer in between 0 and R minus 2. And by the way, this set parameterize the finite dimensional irreducible representations of the quantum group UQSL2C when Q is a Rth root of unity. That's the relationship with representation theory. So we color each edge by a finite dimensional irreducible representation of UQSL2C. And we consider the following state sum. So the summation is over all the possible R colorings. And we sum up the following terms. So first we have a product over all the edges and something, which I'll recall in a second. And then we have a second product over all the tetrahedra of something. Okay? Roughly speaking, these are the so-called quantum integers, the first product. And the second one is the so-called quantum safety symbols. I'll explain all of them, both of them. Okay, so quantum integers, quantum n is the following function of the root of unity q, and here q is a root of unity with certain conditions to be satisfied. And there are two important examples of the root of unity. The first one, e to the pi I over r. For any integer r, that's the one Witten considered. I mean, that's one the Rashtikin-Turaev invariants realize Witten's invariant. Okay? So people always say that this is the one that has physics meaning. I think the precise meaning is that behind everything of this you have a T craft T, and at this particular root of unity, the inner product on the T craft T is positive definite. That's the meaning of having physics. Okay, and the second one is e to the 2 pi of r, where r is out. That's the one we can see the exponential growth. We can talk about the volume conjecture. Okay, and the term in the product in the definition of the Turaev-Viro invariant is, so for that edge E, under this coloring C, it is up to sign plus minus 1, the quantum, the color plus 1. And if you choose this root of unity, then precisely it's just this simple sine function. So sine 2 pi times the color plus 1 over r over sine 2 pi. Okay. Um, that's this term, the quantum integer. Now, and this one is the so-called quantum secret symbol. Okay. So it's a function of these 6 colors on the 6 edges of a tetrahedron. So suppose E1 up to E6 are the edges of this tetrahedron delta. And here the rule is that um, in the first row we have E1, E2, E3, and they are the edges of a face. And then in the second row, you have the corresponding opposite edges. So E1 is opposite to E4, E2 is opposite to E5, and E3 is opposite to E6. Okay? And there are certain symmetries of this quantum secret symbol. They come from the so-called Kleber-Gordon coefficients of representations of UQSL2R. And if you know a little bit of representation theory, you know those coefficients satisfy a million identities, including these two, the orthogonality and the BE identity, or in other words, the pentagon relation. And they correspond exactly to the invariance of the, um, the sum under the so-called this 0, 2 and the 2, 3 partner moves of ideal triangulations. And these are the two partner moves. And partner prove that any two different ideal triangulations of a manifold are connected by a sequence of such 0, 2, and 2, 3 moves. And because of these identities satisfied by the 6 symbols, the state sum in the other page is independent, it's invariant under these moves. So it is independent of the choice of the triangulation. That's why that state sum defines a invariant, topological invariant of the manifold. I know some of you might be wondering like how this quantum secret symbol looks like. Oh, what's the formula? One for is not for ideal triangulation. The one for will introduce a new vertex. Okay, so I don't recommend, but if you insist, the quantum secret symbol looks like this. Okay, so ridiculously enough, on the right hand side, you don't even see the 6 variables because there are like certain linear combinations of the variables. And so the new variables T1, T2, T1 up to T4, and Q1 up to Q3 correspond to the faces of the tetrahedron and the quadrilaterals of the tetrahedron. Okay? So you can still see some pattern from the formula. And I show this slide only because later in our new case, we have a similar formula. Okay? And let's recall the definition one more time. You have you have a huge like state sum over all the possible R colorings, and you take the product over the edges of the quantum integers, so the quantum of the color, and then you have the product over all the tetrahedra of the quantum secret symbols. And due to the identity satisfied by the secret symbols, this is independent of the choice of the triangulation. Okay, example. This is the figure it out, and we need the triangulation. And Thurston tells us that you can do this one. So you take 2 ideal tetrahedra, you remove all the vertices, and then you color the edges and orient the edges as follows. So here all the A's are red and all the B's are blue. In this way, you have a unique way to glue pairs of the faces together, respecting the color and direction of the of the edges. For example, this face must be identified with this one by doing this reflection. And um, for the other faces, there's a unique way to do it. And the quotient space is the figure it out complement. It's not obvious at all. This picture shows why Thurston is Thurston, because and then after gluing you have two edges, namely A and B, and you have two tetrahedral, namely this one and this one. So the Turaev-Viro invariant of the figure out complement looks like this. Okay, so and here is the sum over all the possible colorings from 0 to R. And from this formula, it's not very easy to see the number 2.0298, which is the volume of the figure out complement. That's why volume conjecture is deep. Okay, are there any questions before I move on to the new thing? It's similar to the Color-Jones polynomials, namely the 5-2 knot and the -237 Prezel knot. They have the same volume, but they have different 12-Viro invariants. What do you mean? Closed three manifolds. The same volume, but different. Um, that's a good question, and I don't know. What? Closed manifold. No, I don't choose particular. I sum over all the possible colorings. So the 12-Viro is the norm square of the vector. I think you're talking about the relative Rashtian drive invariant, where you have ambient closed manifold, you have a frame link inside, and you have a coloring on the link. In that way, you can define the relative Rashtian drive. And we have a volume conjecture for that also. And in that case, the coloring may have to do with the cone angles of a cone metric. If the coloring, so if the coloring, if the colors grow linearly in R to some angle theta, then the relative Rashtian drive invariant grows exponentially with growth rate, the volume of a cone metric, hyperbolic cone metric on the knot complement with cone angle the theta given by the coloring. Thank you. Okay, new stuff. So as I mentioned earlier, we define a family of 12-Viro type three manifold invariants using representation theory of a new quantum group, the modular double of UQSL to R, and we understand their asymptotic behavior. So this is a joint work with Liu Tianyue, Ming Shuang from Yumsang, and Sun Xin, who is also here, and Wu Baojun. So Xin and Baojun are probabilitists, and Tianyue is a differential geometry, and Shuang is expert in quantum topology, and I know a little hyperbolic geometry. So we like really come from two different groups, and the relationship between us is through mathematical physics. And to be a little bit more precise, through representation theory of quantum groups, modular double of UQSL2R. I'll see a little bit more later, and the Liouville CFT. If you went to Rami's talk yesterday, and so-called Teichmuller or Virasoro TQFT. And the relationship between these three is very similar to the relationship between the representation theory of UQSL2C, better known as the Rush-Tikin-Turaev theory, and the WZW conformal field theory and quantum trace theory. And among all these, I think these three are mathematically rigorous. So this, to be more precise, is the theory of the so-called positive principal series or positive representations of modular double of UQSL2R. So this thing basically is the tensor product of two copies of UQSL2R, where you have a Q. Let me write a little bit more. Later, you'll see a parameter B in between 0, 1, and Q is e to the pi I b squared. And there's a Q tilde, which is e to the pi I b negative 2. And this modular double is UQSL to R tensor U Q tilde SL to R. Okay. So these representations were first, I think, studied by Faddeev and Teichner and Franco, and maybe I should also put Yip, Ivan Yip, and the Liouville CFT. I think as one of the biggest achievements in the last 10 years in mathematical physics and probability theory. The original like path integral approach of this Liouville CFT was successfully, mathematically, rigorously established using probability theory. So Xin helped me to prepare this sentence. And I just write it down and memorize it and repeat. Okay. For this one, I don't need any help. That's the famous Rush-Tikin-Turaev theory. Okay, so let me start from the very beginning. So we need a special function called the double sign function. So we have a parameter b in between 0 and 1, and we let q be b plus b inverse. And for any complex number z with a real part in between 0 and this b, the following integral defines a holomorphic function. So for such complex numbers, and here z is the variable of the function, and t is the variable for the integral, where the region, the contour omega, is this one. And here you see why we call it omega, because it looks like omega. And we can extend it meromorphically, this function, to the whole complex plane with all the poles on the real line. And actually, we have poles. If you take this exponential, you have poles on the left of 0, and you have zeros on the right of q. And if you don't consider this exponential, you have poles on both the left and the right of both left of 0 and the right of q. Okay. When should I start? 20 minutes. Okay. Okay. So this is the double sign function, and from the double sign function, we can write down the UQSL2R. We can write down the Sigma symbols for the positive representations, which looks like the following. So here we take 6 complex numbers of this form. Namely, the real part is fixed, is 2 over q, and the imaginary part is strictly positive. This space 2 over q plus IR plus is actually the so-called spectrum of the positive representations. This is like in the previous story, we take sum over integers in between 0 and r minus 2, which parameterize the irreducible representations. And here it's an analog of that. And then we can write down this horrible looking function, and that's the Sigma symbol for the positive representations of the modular double of UK. I think this formula was computed by Teichner and the collaborators, Ponsot and whatnot. Please correct me if I'm okay. Where you have you still don't see the variables, but they respectively correspond to the phases and the quadrilaterals. Okay, and instead of a sum, here we have an integral, where the integral is over this. Here I put a straight line, vertical straight line, passing through the interval 3q over 2 and 2q. But we can prove that you can take any curve passing through this interval and asymptotically following the vertical. And the point is that if you look at the integrand, you will see poles here and here. You just want to avoid those poles. Okay. So that's the UQSL2R. We call it UQSL2R Sigma symbols. And it's also worth mentioning that the same formula also computes the fusion kernel of the Liouville CFT. Okay. So that's the relationship between the things I mentioned previously. And I think we're ready to define the invariant. So here we need the, so previously it's only for simplicity, but here we do need the manifold with boundary. We do need the boundary. So we do need the ideal triangulations. And similarly, the same, we have the set of edges E and the set of tetrahedra T. And this time, we call a B-coloring, a assignment of each edge a complex number of this form. So this is the one with real part exactly q over 2 and imaginary part positive. Okay. And later you see that this L, so we write it this way because later you see this L will have to do with edge length of certain triangulation of the hyperbolic structure. Okay. So we color the edges by complex numbers of this form. And let me also mention that the space of all the possible B colorings is this one. Okay. And then similar to the previous one, we take the state. So previously we took a state sum, and here we need to take a state integral. So for any coloring, for any edge E, similar to the quantum integers, here we consider this measure. Previously it's a sine over sine. Here we take sinh over sinh times sinh L times sinh L over B squared. So that's the counterpart of the quantum integers. And for the tetrahedron, we take the B sigma of the 6 colors on the edges. Okay, and then we consider this state integral. So the integral over the space of all possible B colorings, and then the product of this quantity, and then over all the edges, and the product over all the tetrahedra of the Sigma symbols. Okay, and we integrate against dA, which is the product of the imaginary part of the numbers. Now, different from the previous one, which is a finite sum, and experts know that finite sums always converge. Here we have an integral over a, unfortunately, non-compact space. So we have to talk about the convergence. But luckily, this is a finite dimensional non-compact space. So we can talk about the convergence. And that's why that's why we need to put extra conditions, and we have the following result. So if M is hyperbolic with totally geodesic boundary, that means the boundaries are high genus surfaces, and the restriction of the hyperbolic metric on the boundary is a hyperbolic surface. It's a totally geodesic surface. Okay. And if our triangulation T suppose a so-called angle structure, I'll explain what this is in a second. Then we can prove that when the parameter b is small enough, the integral, the state integral, absolutely converges, actually. Okay. And what is the angle structure? Angle structures are defined by Andrew Carson as a tool to find the hyperbolic structure on the manifold. So that's before Hermann's proof of the geometrization theorem. Basically, given a triangulation, you assign the dihedral angles such that you assign the dihedral angles to the tetrahedron, such that around each vertex of the tetrahedron, the three dihedral angles, the sum is less than pi. And that is equivalent to the six dihedral angles of a so-called hyperideal tetrahedron. So you can consider hyperideal tetrahedron as a, let me put it this way. Hyperideal tetrahedron are the building blocks of hyperbolic matrix, such hyperbolic matrix. Okay? And another condition is that around each edge, the sum of the dihedral angles should be exactly 2 pi. Okay? And the relationship between the angle structures and the hyperbolic metric is the following. So if you have a hyperbolic metric, such hyperbolic metric, and if you have a geometric triangulation, meaning each tetrahedron is a hyperideal tetrahedron, then the dihedral angles for that triangulation give us such a angle structure. Okay. And but there are other angle structures than the one coming from the hyperbolic metric. And Carson proved that among all the angle structures, the one that has the maximum volume coincides with the hyperbolic metric, the one coming from the hyperbolic metric. That's how he found, that's his method to find hyperbolic metrics. And but here we notice that we have equalities and strict inequalities. So the space of such structures, if non-empty, it's not compact. So there's no guarantee that such maximum angle structure always exists. But still, it's a very natural structure to consider. Okay? And for the convergence, we need the existence of such structure. So the existence is sufficient. We don't know whether if it is necessary. But once you have an angle structure, your triangulation has an angle structure, then the integral converges. Okay. And the next thing we want to talk about is the topological invariance. So if we compute the thing using two ideal triangulations, do we get the same number? And we can prove the following. If the two triangulations are so-called Kujima triangulations, I'll explain what those things are. Then we do get the same number. Okay? So let me say a few words about the Kujima triangulations. So, of course, the best triangulations to use are the geometric ones. meaning every tetrahedron is hyperideal, is geometric, is positive. But the point is that they don't always exist, or at least we don't know whether they always exist or not. And the closest ones are these Kujima triangulations, which consist of either hyperideal ones, so the good ones, or some flat ones. But the good thing is that they always exist. We can always find such triangulations. And there are in total finitely many of them. They come from a subdivision of a so-called Kujima polyhedral decomposition. And this is a counterpart of the famous Epstein planar decomposition, or the Delaunay decomposition for cusp manifold. Okay, so they're very natural constructions. And another important thing is that such Kujima triangulations always support angle structures. That means all these integrals converge. Okay? All these are finite numbers. And for these triangulations, you can also see edge lengths, which are important for the asymptotics later. Okay? And for Kujima triangulations, we can show that it is independent of the choice of those. And because of this, we can now define our invariant. So for hyperbolic three manifold with totally geodesic boundary, the Bth UQSL2R Turaev-Viro invariant of the manifold is defined by such state integral, where for T, we just choose a Kujima triangulation. So it converges and it's independent of the choice of such triangulation. Okay? And we strongly believe that it should be defined for all the parameter B, not just for the sufficiently small ones. And more importantly, we believe that for any ideal triangulation supporting a angle structure, the value should be the same. We don't even need to choose the different. We just cannot prove it yet. So that's the definition. And so far, it seems that for the new environment, nothing is better than the old one. Because for convergence, we need the conditions. For topological invariants, we need conditions. And so what's good about the new one? As I mentioned earlier, we have a better understanding of the asymptotics. Oh, yes, it satisfies the actually both the orthogonality and the pentagon relation. But the problem is that from the identities to the invariants, there are certain switch of the order of the integral involved. And to make sure that you can do that, you need absolute convergence of the integral. You need the Fubini theorem. And for that, we need the extra conditions. Yes, but that's integral over one variable. Which Kashaf invariant? Oh, Anderson-Kashaf. We believe that they belong to the same TQFT, the Virasora or the Teichmüller TQFT. But so the Anderson-Kashaf is like the Rashtigan-Turaev for that TQFT, for not complement or cusp manifold. And here, first of all, we consider manifold with totally geodesic boundary. And our invariant is Turaev-Viro type. The definition looks not similar. I mean, both are state integral, but exactly, yes, that's, yeah, but yeah, that's If you look at the Rashtin and Turaev-Viro, they are also similar. Both are state sounds. One uses Kirby color, the other uses CK symbol. Yeah, so they should be related. Yes. What's your question? Yes, for cusp three manifold. Uh, different setting. But the underlying TQFT should be the same, we believe. Yeah. Okay. So asymptotics, this we have this. So the difference is that this time as b goes to 0, the invariance decays exponentially with decay rate, the hyperbolic volume. And if you look at so-called one loop term, you see the adjoint twisted right muscle. Um, okay. And in particular, if you only care about the exponential decay rate, that's the hyperbolic volume. And as a possible application of our invariant, the same. There's a symmetry between B and 1 over B. Together with our theorem, if the remark was true that the invariant is really independent of the choice of the angled triangulations, then we may give a affirmative answer to a conjecture of Cousin on the angle structures that um, the maximum volume angle structure, the maximum of the volume of the angle structures must be at most the hyperbolic volume. And we also hope that since here we already have the asymptotics, we hope to this can help to understand the asymptotics of the more classical invariants like Color-Jones, the Kashaev's volume conjecture, or the volume conjecture of the Rashid and Turaev invariants. I think that's all I want to say for today.
Let's thank the speaker. Questions or comments?
Mm-hmm. We can so when B square is irrational, I think we don't have the representation theory, but we can define the invariant by continuity argument. That's that's very possible. That's highly possible. I tend to believe that might be possible. That's possible.
So you have identities which relate two representation theories. One is quantum group for root of unity. Another is this positive representations.
We have identities.
I mean volume conjectures and everything. So um, that's identities between where the left-hand side is one class of representation, the right-hand side is another class of representation. So do you know how to see the relation of representation theories more directly?
No.
Because then you can generalize it to higher ranks, etc.
My collaborators may know something about it.
So you're saying that there are some relation between this like root of unity representation and the yeah. So this is something we hope to understand, but I mean so
So I know there are certain relations between the B secret symbols and the other secret symbols. We'll move the parameters to the rational numbers, and by computing certain residue, you see.
Yeah, so we also think that there are some relation, and eventually our invariant would be also somehow related to this
Right,
class of
yeah.
invariants. But the existing literature on these quantum groups are not easy to understand. We are still on at the stage of trying to make sure that everything written down we can cite it and so on.
Yeah, that's actually exactly the hope.
Other questions? If no, let's thank the speaker. And the next talk starts